Volumes with known cross-sections. Cross-section. A cross-section of a solid object S is the plane region formed by intersecting S with a plane. Informally, a cross-section is a slice of a three-dimensional object. This is probably best understood by looking at a picture. So here I have a solid object S and a cross-section located at this value X here can be obtained by thinking about taking just a sheet of paper and slicing this particular solid. So right at this location X, my cross-section appears to be a square, and we're going to call the area of that cross-section A of X. It's dependent upon the X value location that I decided to take my slice. Here I have a second solid, and this time the cross-section at this location here X is a triangle instead. So we can see that the cross-section's area is going to vary based on the value of X chosen. So if I chose my X location over here, I still have a triangular cross-section, but the area is different. We're interested in finding the volume of these three-dimensional objects. To find the volume of the solid, we can think of adding infinitely many of these infinitely thin cross-sections together. So we are taking the limit as n approaches infinity. N is the number of cross-sections. So if the number of cross-sections goes to infinity, and we think about adding, so summation notation, we're adding all of those areas together. So if we add these infinitely many, infinitely thin cross-sections together, we will obtain the exact volume of these solids. Let's go ahead and extend the previous idea. Volume with cross-sections perpendicular to the x-axis. Suppose that a solid body extends from x equals a to x equals b. Let a of x be a continuous function that gives the area of a vertical cross-section at x, perpendicular to the x-axis. Then the volume of the solid is given by v equals the integral from x equals a to x equals b of a of x dx. So again, looking at the previous image, if we want to find the volume of the solid extending from x equals a to x equals b, then we need only find a way to represent the area of a cross-section as a function of x. And then we're going to set up this definite integral which will yield the exact volume of the solid. Let's go ahead and look at our first example. A shape is formed by taking infinitely thin squares and stacking them up perpendicular to the x-axis with base formed by the lines y equals 1/2 x, y equals negative 1/2 x, and x equals 2. Find the volume of this shape. Let's start by constructing the base and sketching these three lines. Here I'm going to go ahead and label them as y equals 1/2 x, y equals negative 1/2 x, and x equals 2. So this is going to be the base of my solid, and I'm told that the cross-sections are going to be squares that are perpendicular to the x-axis. I'm going to construct one of these squares at this generic location x. So I'm going to create a square that is perpendicular to the x-axis. Remember, this square is coming out at us, so it's going to make a three-dimensional object here. I'm going to try to make it look like it's popping out of the screen a little bit. So here is my square, not quite perfect. And notice that the side of the square here touches both the top and bottom function here, and that's the side length of the square. So I'm going to go ahead and call that S of x. That's going to be this length right here that's happening at x. Now let's go ahead and apply our volume formula. The volume of this solid is going to equal the integral from x equals a to x equals b. Our limits of integration are coming from the x-axis. This region extends from x equals 0 to x equals 2. And the area of my cross-section is side squared. The area of a square is side squared. So here I'm going to go ahead and write brackets squared dx. What goes inside those brackets is s of x. S of x being the side length at any particular x. So what's going to go right here is my side length as a function of x. Well, that's obtained by doing top minus bottom. So 1/2 x minus negative 1/2 x. So I like to include variables in my limits of integration because I want to make sure that I'm consistent throughout the problem, that I'm using the same variable. So here I have 1/2 x minus negative 1/2 x, which combines to just be x squared dx. So the integral that I'm evaluating is simply the integral from 0 to 2 of x squared dx. So now the antiderivative is x cubed over 3 evaluated from 0 to 2. So 2 cubed over 3 minus 0 cubed over 3 is simply 8/3. Because we're finding a volume, our units would be units cubed. Volume with cross-sections perpendicular to the y-axis. Suppose now that a solid body extends from y equals c to y equals d. Let a of y be a continuous function that gives the area of a horizontal cross-section at y, perpendicular to the y-axis. Then the volume of the solid is given by v equals the integral from y equals c to y equals d of a of y dy. So notice the only difference here is that the volume formula is in terms of y, and that's because our cross-sections are perpendicular to the y-axis. So our limits of integration are y values, so y would extend from y equals c to y equals d, and our cross-section would have to be written as a function of the variable y. In this example, we're told the base of a solid is bounded by y equals x cubed, y equals 0, and x equals 1. Sketch the base region and set up the integral needed to find the volume V of the solid with the following cross-sections. In part A, we're going to have semicircles taken perpendicular to the y-axis. We'll start by constructing the base. The base is bounded by y equals x cubed, y equals 0, and x equals 1. So y equals x cubed passes through 0, 0, and 1, 1, and has this general shape. So I have y equals x cubed. Y equals 0 is simply the x-axis. And then x equals 1 is a vertical line at 1. So I have x equals 1. So this right here is my base region. And I'm told that my cross-sections are semicircles that are perpendicular to the y-axis. So I'm going to go ahead and sketch one of these cross-sections. So perpendicular to the y-axis is going to make my shape look something like this. This is my semicircle that again is sort of popping out of the base to create a three-dimensional solid. And so this cross-section here, this base of my cross-section is actually the diameter of the semicircle. So I'm going to have to represent the diameter as a function of y because my cross-sections are perpendicular to the y-axis. And this is going to extend from y equals 0 to y equals 1. Because remember, my limits of integration now have to be y values. So let's go ahead and start to find our volume by applying the formula here. So our volume is going to equal the integral from y equals 0 to y equals 1. And then we're going to need the area function for a semicircle. Well, a semicircle is 1/2 pi r squared. So I'm going to go ahead and put 1/2 pi, and then I'm going to leave a big blank space for a second, squared dy. So what's going to have to go right here is the radius as a function of y. So here, this is the diameter as a function of y. So I'm going to have to find the diameter as a function of y and cut it in half to find the radius as a function of y. So I'm going to go ahead and just start by putting over 2. So what's going to have to go in the numerator here is the diameter as a function of y. Well, this diameter is going to be obtained by doing the right function minus the left function. Well, the right function here is x equals 1, so I'm going to have 1 minus, and now here we have to be incredibly careful. So here, if we were to just think that the left function over here is x cubed, and we put x cubed right here, that would be incorrect because we need everything to be in terms of y. And that's why I try to keep the habit of starting with variables in my limits of integration. I have to rewrite this function in terms of y. So if I take the cube root of both sides, I'll have x equals the cube root of y. So my diameter, right minus left, is 1 minus the cube root of y. So this right here is my radius. So it's the diameter as a function of y over 2. So this is my answer for this problem because we were simply asked to set up the integral needed to find the volume V of the solid. In this example, we're going to use the same base, but this time the cross-sections will be isosceles right triangles with base as the hypotenuse taken perpendicular to the x-axis. So I'm going to go ahead and construct one of these isosceles right triangles. So here I'm going to pick some generic x value and construct my base that is perpendicular to the x-axis. So this is going to be a isosceles right triangle. So this is a right angle right here, and we're told that the hypotenuse lies along the base of the region. Alright, so we'll go ahead and start to apply our volume formula here. So our limits of integration will be x values. So we're going to have x equals 0 to x equals 1. And we're going to need to find the area of an isosceles right triangle here. So this, again, is the hypotenuse. So this is the base of my triangle. So I'm going to go ahead and call it b of x. And we can find that doing top minus bottom. So that would be x cubed minus 0. So the formula for a triangle in general is 1/2 base times height. So my base will be x cubed minus 0. So this is b of x. And then what's going to need to go right here is the height as a function of x dx. So we have 1/2 base times height. Here's my base. I need to go ahead and think about what is my height going to be for this particular isosceles right triangle here in terms of x. So I'm going to go ahead and construct my right triangle over here, my isosceles right triangle, so we can get a better sense of what's going on. So this is my base, b of x. And this is an isosceles right triangle, so that means that if this is 90, then these two are each 45 degrees exactly. And I'm interested in finding the height, h of x. So here, if I go ahead and construct this perpendicular, this angle bisector here, this is going to be 90 degrees, and if this angle right here in the corner was 45, this angle up here must also be 45. In other words, this is also a isosceles right triangle, so that means these two side lengths are the same. Well, if I cut this base in half here, then this is b over 2, so that means that the height is also b over 2, or b of x over 2. So that's what I'm going to go ahead and fill in right here for h of x. It's going to be the base over 2. So it's going to be x cubed minus 0, the base, divided by 2. And we'll go ahead and clean this up a little bit. This is going to be the integral from 0 to 1, and then we have 1/2 and then another 1/2 over here, so we have 1/4, and then we have x cubed times x cubed, that's x cubed squared, dx, or x cubed squared is just x to the 6th dx. So this is the integral that will find me the volume of the solid. In this example, we have a solid is formed with circular discs as cross-sections perpendicular to the x-axis whose diameters run from the parabola y equals x squared to the parabola y equals 2 minus x squared. Set up the integral needed to find the volume V of the solid. So we'll go ahead and zoom in on the picture. So here we have our disk, and we're told that the diameter, so I'm going to go ahead and mark the diameter here, extends from x squared to 2 minus x squared. And I'm going to go ahead and call the diameter here d of x. So the diameter would be top minus bottom here, so it looks like it would be 2 minus x squared, or 2 minus 2x squared would be the diameter of my disk. So we're going to go ahead and find the volume of the solid obtained by having these cross sections where the diameters go across this base region. So now we're going to go ahead and start to set up the volume formula. The volume is equal to the integral from x equals, so we need to know the x values that this region extends, and that's going to be finding the x values of the points of intersection here. So remember, if we want to find the point of intersection, or points of intersection, we're going to need to set the two functions equal to one another. So we'd have 2 equals 2x squared, or x squared equals 1, so we get plus or minus 1. So our limits of integration are going to extend from -1 to 1. And our cross-section is going to be a disk, which is really just a circle. So here we can see that it doesn't look like a circle. We can see here a disk with a height involved, so like a little cylinder with a height. But as we saw, we're going to go ahead and think about these as infinitely many, infinitely thin cross-sections. So we are going to have the area of a circle here as our area function. So the area of a circle is pi r squared. So I'm going to leave pi, I'm going to leave a big space for r squared. So what needs to go right here is my radius as a function of x. Well, here we found that this was going to end up being the diameter. So the diameter, 2 minus 2x squared, is going to have to be cut in half to find the radius. So my radius is going to be 2 minus 2x squared over 2. And then we have dx. We want to make sure that we're all the same variable here, our limits of integration and our integrand and our differential. So this is going to be the integral needed to find the volume of this particular solid. So if we clean it up just a little bit, we have the integral from -1 to 1, and then we have pi over 4, and then 2 minus 2x squared dx. So the 4 is coming from taking the 2 and squaring it and bringing it to the outside, and then I left the 2 minus 2x squared, quantity squared, here. So evaluating this definite integral will give us the volume of our solid. Now, when solids are formed by cross-sections that are circles, we can think of them as being created by rotating or revolving a two-dimensional region about an axis. And these are called solids of revolution, which is what we're going to go ahead and study next. Solids of revolution, the disk method. Take a minute to clear your mind and imagine revolving the shaded region around the x-axis. Try to visualize what this three-dimensional solid will look like. So we're taking this region here, extending from 0 to 2, and rotating it around the x-axis. Imagine what that three-dimensional solid will look like. Is this the figure you imagined? Notice that the shape of the cross-section is a circle. So here at this x value, we can see that a cross-section would be a perfect circle, and notice that its radius, r, would extend from the x-axis to the function y equals x squared. Let's go ahead and generalize this. Volume of a solid of revolution, the disk method, cross-sections perpendicular to the x-axis. If f of x is continuous and f of x is greater than or equal to 0 on the interval from a to b, then the volume obtained by revolving the region under the graph about the x-axis is given by, so here the volume is still going to be equal to the integral from a to b of the area function in terms of x dx. But the area is going to end up looking like a circle. So if we take a region that's above the x-axis and continuous, and we think about rotating it around the x-axis, the cross-section will look like a circle. So the area of a circle is pi times the radius squared. So the radius needs to be a function of x. So here, this is going to be my r of x. So notice that it's obtained by doing top minus bottom. So the top function is f of x, and the bottom is the x-axis, which is just y equals 0. So the radius r of x is top minus bottom, or f of x minus 0. So we have that the integral from a to b of pi times f of x squared dx gives us the volume of a solid of revolution using this disk method. So this will yield the volume of this solid. So r of x is the radius of the circular cross-section at different values of x. In this example, let's find the volume V found by revolving the region bounded by the x-axis, y equals x squared plus 1, x equals -1, and x equals 1 about the x-axis. So we'll start by constructing the region we're going to revolve. So we have x squared plus 1, so we have this parabola that shifted up 1 unit, and we also have the vertical lines at 1 and -1. Oops, so I missed a little bit. And we have bounded by the x-axis as well. So the region that we're rotating is this region here. And I would always recommend sketching the region, and if you have one, using a highlighter to highlight the region that we're rotating. So we're rotating this region around the x-axis, so I like to use a little circular arrow to indicate what line we're rotating around. So now the cross-sections are going to look like circles. So we can still think about constructing a cross-section as some generic x. So the cross-section would look like a circle when we revolve around the x-axis. And that radius would be top minus bottom. So this top function here was x squared plus 1, and the bottom function here is just y equals 0. So let's go ahead and set up and then find the volume. So we're going to set up the integral. The volume is x equals -1 to x equals 1. So we can see those are the x values my region extends from. And then we're going to have pi times the radius squared dx. So the radius, as we said, this is r, is top minus bottom, so just x squared plus 1 minus 0, or just x squared plus 1. So this is going to give us our volume, so now we'll go ahead and evaluate this definite integral. So I'm going to start by factoring out a pi times the integral from -1 to 1 of x to the 4th plus 2x squared plus 1 dx after distributing. And now what I want to recognize is that the integrand is an even function. So instead of evaluating the integral from -1 to 1, I can think about this as 2 pi times the integral from 0 to 1 of x to the 4th plus 2x squared plus 1 dx. so that now when I find the general antiderivative, substituting 1 and 0 in will be a little bit less computational work. So I have 2 pi that I'm going to leave on the outside. The antiderivative is x to the 5th over 5 plus 2x cubed over 3 plus x evaluated from 0 to 1. Well, now I can just think about plugging in 1 because plugging in 0 into the polynomial will just give us 0. So we have 2 pi times 1 over 5 plus 2 over 3 plus 1. And we'll go ahead and simplify this all the way. I have 2 pi, and then I'm going to have a common denominator of 15. So 3 over 15, 10 over 15, and 15 over 15. And that's going to give me 2 times 28, so we're going to have 56 pi over 15. And again, we are finding a volume, so here it would be units cubed. I want to take a second to go back and look at the region that we're rotating and notice that we have symmetry involved, and that if we took the integral from 0 to 1 and found the volume of rotating that region and doubled it, that we would get the same answer, which again is what we did over here when we thought about changing those limits of integration, because this is an even function from 0 to 1, and doubling that particular integral. We would see as an indication to do that as well because of the symmetry involved in the region that we're rotating. In this example, we'll find the volume V of the region found by revolving the area bounded by the y-axis, y equals x cubed, y equals 1, and y equals 8 around the y-axis. We'll start by sketching the region. So here's our region. We have y equals x cubed, and then y equals 1 and y equals 8 are horizontal lines, and the y-axis, and we're rotating this region around the y-axis. So this time our cross sections are going to be perpendicular to the y-axis. So if I think about rotating this, I would have my cross section as a disk that is perpendicular to the y-axis. So here is the radius of my disk that extends from the y-axis to my function, y equals x cubed. So my limits of integration are going to have to be from the y-axis are going to have to be y values. So we're going to extend from 1 to 8. So I'm going to set up the volume is the integral from y equals 1 to y equals 8 of pi times my radius squared dy. Well, my radius is going to be obtained doing right minus left. And we have to be in terms of the variable y. So I have to solve here for x. So x is equal to the cube root of y. So I'm going to have the cube root of y minus 0. So I have the cube root of y minus 0, quantity squared dy. So this is the integral that's going to find my volume, and now all that's left is to evaluate it. So I have the integral from 1 to 8 of pi times y to the 2/3 dy. So that's rewriting y to the 1/3 and then multiplying by 2. So I'm going to go ahead and take out the pi and find the antiderivative of y to the 2/3, which is going to be y to the 5/3 times 3/5 evaluated from 1 to 8. So we'll go ahead and substitute in 8 first. So I'm going to have 3 pi over 5, 8 to the 5/3 minus 3 pi over 5, 1 to the 5/3. And so evaluating 8 to the 5/3, that's the cube root of 8, which is 2. 2 to the 5th is 32. So 8 to the 5/3 is 32. So we're looking at 3 pi over 5 times 32 minus just 3 pi over 5, because 1 to the any real number is just 1. So here I'm going to have 96 pi minus 3 pi. That's 93 pi over 5. And again, this is a volume, so we'd have units cubed. Solids of revolution, the washer method. Take a moment to imagine revolving this shaded region around the x-axis. What would this three-dimensional solid look like? So we're talking about this region here in quadrant 1, bounded on the x-axis between a and b, and between these two functions f of x and g of x. So notice that this time the region is not right up against the axis of rotation. It's not right up against the x-axis. So we have this gap happening. So try to imagine what rotating this around the x-axis would look like. This figure is a bit trickier than our previous solids. Notice that the shape of the cross-section is a washer. So we're thinking about the tool, the piece of hardware, a washer, because of that gap. So if I focus on one particular x value between a and b, at that x value, if I think about this lined segment here that's drawn between the point A and the point B, if I think about taking that and rotating around the x-axis, the cross-section that is formed is that piece of hardware, a washer, right? And so this integration process is going to have us add up the area at each x value between a and b to form the volume. So the solid has this big hole in the middle of it, right? So if we look at it from the sideways perspective, we have that circle within a circle. So what we're going to need is two radii. So we're going to need to find the area of the outer circle using the big radius minus the area of the inner circle using that small radius. And then we're going to use that integration process to add up all of those areas to find the volume of the solid. Let's take a moment to formalize the formula for finding the volume of a solid of revolution using the washer method, where the cross sections are perpendicular to the x-axis. So the washers are stacked vertically, extending from x equals a to x equals b. What we need is two functions, f of x and g of x, that are continuous, and f of x is greater than or equal to g of x, and both of them are positive. So f of x is above g of x, and both are above the x-axis on the interval from a to b. Then the volume obtained by revolving this region between the graphs about that x-axis is going to be found by doing the integral from a to b of pi times the big radius squared dx. So the big radius here extends from the axis of revolution all the way to that farthest away function here, f of x. And so if we find this first integral, that's using the disk method. So we're finding the volume of this solid that doesn't have a hole in it, but now we have to carve out that hole. So we have to subtract this other integral, the integral from a to b of pi times that smaller radius squared dx. So that smaller radius here, the radius extends from the x-axis to that closer function g of x, that's the smaller radius. So we're going to find the volume of that solid and carve it out, which is why we're subtracting it. So it's doing two separate integrals, but because we have the same limits of integration on each, we can actually combine it together. So the big radius I'm calling capital R of x, the small radius lowercase r of x. They both have a pi, which is a constant multiplied in the integrand. So I pulled out the pi, and again, because they're the same limits of integration, we can combine the integrand to be capital R of x squared minus lowercase r of x squared. So this is sort of the really general formula that we can use, and then our goal is going to be to find capital R of x and lowercase r of x. What's that big radius and what's that small radius? And if we're rotating around a horizontal line like the x-axis, we can think about finding each of those as a top minus bottom situation, top function minus bottom function. So for this problem, the top function up there is f of x. So f of x minus 0, the x-axis is 0, so we have f of x squared. And then the smaller radius, top minus bottom, is g of x minus 0. So the formula for here, this setup, is pi times the integral from x equals a to x equals b of f of x all squared minus the quantity g of x squared dx. So again, capital R of x is that outer, that bigger radius of the circular cross-section, and lowercase r of x is the inner or smaller radius of the circular cross-section at different values of x. Let's look at an example. We want to find the volume of the region found by revolving the area in the first quadrant, bounded by y equals the square root of the quantity 4 minus x squared, y equals x, and the y-axis around the x-axis. We need to start by finding this area that we are rotating. So let's graph the square root of quantity 4 minus x squared, which is a semicircle on top of the x-axis with a radius of 2, the line y equals x, and then the y-axis. Here are my graphs, and the region that's bounded by all three functions is going to look a little bit like a pizza slice or a pie slice here. So we're bounded in quadrant 1, and we're bounded by the y-axis, y equals x, which is just a line passing through the origin with a slope of 1, and then that semicircle on top of the x-axis with a radius of 2. All right, so we are going to be rotating this around the x-axis here. So how do we know that we have a washer method as opposed to a disk method? So if there's any type of gap, if there's any gap at all between the region and the axis of rotation, then we're going to have a washer method situation. So that's why it's important to draw the region very precisely and highlight the region so that we can see if there is this gap between the region and the axis of rotation. And so let's go ahead and get started. So we're going to have the volume is, I'm going to leave the pi on the outside, pi times the integral from x equals 0. So 0 is that x value that we are starting at, but we actually don't know the other limit of integration because we need this point of intersection here. So I'm just going to leave it as x equals for a moment. And then what we're going to need is that big radius squared and the little radius squared. So I like to think about that again as going from the axis of rotation to that sort of farthest away function there and thinking that's my big radius, right? So that's going to form its own solid when rotating that doesn't have something carved out of it yet. And then I have to figure out, well, what's that part I have to carve out? So I start from that axis of revolution and I think about what's that closer function. So that's going to be here. Whoops. So that's going to be here. This is going to be my little radius. This is going to be my little r. So I need that big radius squared minus the little radius squared. That's how I like to think about it. So my big radius, top minus bottom, is the square root of 4 minus x squared minus 0, because the bottom of that big radius is the x-axis, and that is just 0. So all of that gets squared, minus the little radius. And so the little radius there is top minus bottom, so the top is x. So we have x minus 0, which is just x squared. So all of that dx. So the only thing that we're missing is the other limit of integration, which we find by setting those two functions equal to each other. So we're going to do sort of that scratch work where we solve 4 minus x squared is equal to x. We'll square both sides. 4 minus x squared is equal to x squared once I square both sides and eliminate the square root. I have 4 equals 2x squared once I add the x squared to the other side. If I divide by 2, I get 2 equals x squared. And then solving for x, I'm going to get plus or minus the square root of 2. So there's 2 solutions because there is another place where if this circle was completed, if I had the entire circle instead of the semicircle, the line would intersect again down here. But we're only thinking about quadrant 1 right now, so we just need positive the square root of 2 as our other limit of integration. And so that is the setup now to finish, to get a numerical value for this volume. I'm going to simplify the integrand so I can take the first part and get rid of the square root because of the squared that's happening here. So I have pi times the integral from 0 to rad 2 of 4 minus x squared and then minus x squared dx. So pi times the integral from 0 to rad 2 of 4 minus 2x squared dx. So not too bad to integrate here. We're looking at 4x minus 2x cubed over 3 evaluated from 0 to the square root of 2. Now thankfully on this problem, plugging in 0 into each of these terms, we'll just get rid of those terms. So we're really just thinking about plugging in the square root of 2. So I have pi times 4 rad 2 minus 2 rad 2 cubed over 3. That's going to be pi 4 rad 2, and then what's happening here, if I square the square root of 2, that's going to give me a 2 to pop out to multiply to this 2, and so one copy of rad 2 is going to be left there because there's 3. I'm multiplying it by itself 3 times, so multiplying it by itself twice will give me a 2, so this is going to be 4 rad 2, so minus 4 rad 2 over 3. And so if I make common denominators, multiply the bottom by 3, that would make this a 12. So we're looking at 12 rad 2 minus 4 rad 2 over 3, that's 8 rad 2 over 3. So 8 rad 2 over 3 pi. 8 rad 2 over 3 pi is my volume. So note, it is possible to revolve a region about a horizontal or vertical line other than the x-axis or let's say the y-axis, right? So the horizontal or vertical line we revolve a region about is called the axis of rotation, or sometimes it's called the axis of revolution. So just formalizing that, I have said that out loud already, but that line that we rotate around can be either the x or y axis or really any horizontal or vertical line. Let's look at another example. This time we're just going to set up the integrals needed to find the volume V of the solid generated by revolving the regions bounded by y equals x and y equals x squared about the line y equals 2. Let's start by drawing our functions. We have y equals x. That's just, again, the line passing through the origin with a slope of 1. So let's see. We have y equals x. And then y equals x squared, that's just that parabola, also passing through the origin. And the point 1, 1 and the point 2, 4, that's going to be off the graph here. But I'm going to make sure and sketch this as a parabola here. And so it does continue to the other side, but we want the region bounded between these two functions, which is just this little sliver here that's in quadrant 1. And we can see that these intersect at 0, the origin, and at that x value 1. So by drawing a detailed graph, we found those points of intersection. We were able to. And so we are rotating this time around a different line, not the x or y axis. So we're rotating around the line y equals 2. So here y equals 2 is a horizontal line, and it happens to be above the region that we're rotating, but that's okay. We can still do that. So we want to identify whether we're going to be using the disk or washer method here. And so since we've clearly shaded the region that we're rotating and it's not right up against the axis of rotation, in fact there's a huge gap here, this is going to be a washer method. So we're going to have this big radius and this small radius involved. So let's get started with our setup. We have volume is equal to, pi, put the pi in the front, pi times the integral from x equals 0 to x equals 1. Since these washers are going to be stacked vertically, we're going to be integrating everything with respect to x. So we're extending from x equals 0 to x equals 1. And we need that big radius and that little radius so that we could take each one and square them and subtract. So I like to start by going to that axis of rotation or axis of revolution and going to the farthest away function, because that's going to give us the biggest radius, right? So from the axis of rotation to the function that's farthest away, that's going to be my big R, right? So to find that big radius, we're going to do top minus bottom. So we're going to do, in this case, 2, and then minus, well, what's that bottom function there? A really good habit to sort of start is to label the equation close to the graph, right? So that you can kind of easily identify it. So we have 2 minus x squared is my big radius, and then my little radius. So from the axis of rotation to that closer function involved in the region that we're rotating, that's going to be my little r. And so the top of that little radius is 2, and the bottom of that is going to be x, because this line here is y equals x. So it's going to be 2 minus x. So that's my big radius and my small radius, right, across the entire interval from 0 to 1. The bigger radius and the smaller radius are going to stay the same. So when we set this up over here, I'm going to have the quantity 2 minus x squared minus the quantity 2 minus x squared. So that's my big R squared minus my little r squared. And we're integrating with respect to x. Now there is a part B to this problem where we're still going to take that same region bounded between y equals x and y equals x squared, but this time we're going to set up an integral to rotate around the line y equals -1. And so y equals -1 is a horizontal line, but it is below the region that we are rotating. So what we're going to do to start to set this up is we're going to have that the volume is equal to pi times the integral from x equals 0 to x equals 1 again. So the limits of integration are determined by the region that you're rotating, right? And they're x values because our cross sections are perpendicular to the x-axis, right? We're envisioning adding up from x equals 0 to x equals 1, all of these quote-unquote areas, right? These really skinny slices, these areas, and we're adding them all up from 0 to 1. And so we just need to find the area of that outer disk and then minus the area of the inner disk, because that's going to carve out that inside. So to find the big radius, we start from the axis of rotation, which is again below the region this time, and we go to the furthest away function, and we call that capital R. All right, so the furthest away function in the region this time is x. So the radius, we're going to always find doing top minus bottom, and so that's going to give us x minus -1. So x minus -1 is going to give us an x plus 1. And then to find the smaller radius, we start from the axis of rotation, we go to the closer function for the region, and that's going to be x squared. So little r, right, the little radius that we're going to carve out, is top minus bottom, so we have x squared minus -1 again. So x squared plus 1. Right, so we're always going to do that top minus bottom because, you know, we're thinking about how these represent numbers. So we're going to take the positive value, right, and subtract the negative value to find that distance. So if we wanted to find the distance between 2 and -1, so I'm just putting specific numerical values on this, right? So 2 to -1 is a distance of 3, but we would find that by doing 2 minus -1, and that's going to give us 2 plus 1, which is 3. Right, so that's why we're kind of always doing that top minus bottom situation when we have a vertical line to find the distance, right? That's what we're trying to do, is find distance. So let's set this up. We have the big radius, that was x plus 1 squared, minus the little radius squared, that was x squared plus 1 squared. And we're integrating with respect to x, so that's my big R, and that's my little r.